Well, hello, chemistry students. This is Mr. Kinney. We're going to go over the chemical bonds review sheet, questions 1 through 30. This is part 1. And let me zoom out here so we can see a little bit more. And to begin with, what is the charge on an aluminum ion? Well, I think the best to start here, let's write the Lewis structure for aluminum. It's in group 3, group 13, or as I like to call it, 3-tene. Okay, so that means it has 3 valence electrons. And so we're going to put 1, 2, 3. Now, aluminum, as all metals, they want to lose their electrons. Way easier to lose 3 than to gain 5 more. So that electron is going to leave. That electron is, and each of those electrons have a negative charge. So what happens is when those, I'm going to draw an arrow here, when 3 electrons leave, because aluminum will throw them off, you're going to end up with aluminum plus 3, because now it has 3 more protons in its nucleus, then it has electrons in its shell, and it becomes an ion. So it has ionized, and that's what we talk about when something ionizes. It's either gained or lost electrons. Metals ionize to become cations, and nonmetals will ionize to become anions. The octet rule. Okay, octet, 8. Okay, so let's just call it the 8 rule. States that chemical compounds, atoms tend to have in chemical compounds, atoms tend to have, they want to have 8 electrons around them. Okay, so for example, well, like let's go to our friend aluminum over here. Right here, aluminum has those 3 electrons over here. It needs 8 electrons to be stable. But hey, atoms are lazy, so aluminum is just as happy to much happier get rid of those 3 electrons. So now it may only have, it's got rid of its electrons in its 3rd shell, but now it's got its 2nd shell is totally filled with 8 electrons, because if you have 8 electrons in your outermost shell, you are stable. So atoms tend to have 8 electrons. There will be an exception, and we do know that hydrogen and helium, since they only have a 1s orbital, off the paper there, sorry. Since they only have hydrogen and helium, they only have a 1s orbital. The maximum they can have is 2 electrons. So they're the exception to the octet rule. I guess you'd call them the duet rule, okay? So, number 3. How many electrons does barium? All right, first let's find barium. Oh, there it is right over here. It's in group 2. So barium is Ba. So let's see, how many electrons? Here's barium, and I'm going to draw its Lewis structure because it has 2 valence electrons because it's in group 2. How many, let's see, how many electrons does it give up to achieve noble gas? Well, barium will lose 2 electrons. It wants to get rid of those. And now it's going to become a +2 ion. Now let's take a look on the little periodic table here. Zoom out a tad so we can see. So over here, here's barium sitting down here. When it loses these 2 electrons it has, it's going to think that it is now xenon. So it's going to try to behave just like xenon, having 8 electrons in its outer shell now, except the trade-off that it gets for being xenon-like is it's got a pretty big charge attached to it. +2, it's going to be attracted to negative ions. So it's kind of stable now, but it's got an attractive force. What is the formula for an ion formed when potassium, okay, so, that'd be oxygen, okay. Potassium's over here. Now be careful, okay, just because it's potassium, don't go put down P, that's phosphorus, okay? So potassium, look it up on your periodic table, okay, here's potassium over here, okay, it's in group 1, so it has 1 valence electron. And what is the formula when it achieves noble gas configuration? Well, it's going to lose that electron, so I'm going to show an electron coming off, it's going to get rid of that, and it's going to still be the K, but now it's lost a negative charge. So now it only has 18 electrons, and if it has 18 electrons, it thinks it's argon, okay, but it has that positive charge, so it's an ion, okay, so it thinks it's argon. Thinks it's argon, but it's got a plus charge. How many electrons does nitrogen gain? Okay, here's our friend nitrogen. Now, nitrogen's a nonmetal, so when we're on the nonmetal side of the periodic table, these guys gain electrons, and over here they lose electrons, or throw them at you if you want to think of it that way. So nitrogen is in group 15. So when we draw its Lewis structure, it'll be like that. And to become stable, it needs to get 3 more. I'm going to draw those 3 as a negative sign because just to remind you now, okay, that, I mean, we could do the Lewis dot, but I want to emphasize here that it's got a negative charge. So it's got 3 extra negative charges, so that's going to, we're going to call it a -3 anion. And again, remember my stupid memory clue, which isn't stupid if it helps you, an anion, think if I make an A with a big negative sign, is negative, whereas potassium over here is a cation. I put that big plus charge on there, and so that can help you remember what a cation is and an anion. If you draw the minus sign, they're really big. Did I answer this question? How many electrons does nitrogen gain in order to achieve noble gas configuration? Nitrogen has to gain 3, so it's got to get 3 electrons. Hey, look it over here. Our friend aluminum is getting rid of 3. If aluminum and nitrogen get together, they can make a pretty good pair because each needs to gain or lose 3 electrons. And at that point, nitrogen now thinks when it gains those 3 electrons, like 1, 2, 3 more, it thinks it's neon, but it's neon with a +3 charge, so we call that nitride. How does an ionic bond occur? Well, just as we've been talking here, when you gain or lose electrons. Gain or lose electrons, you are going to become an ion. So that's what an ion is. You gain or lose electrons. And they do that because they want to be stable. Okay, sorry for the, oh, that's terrible. Sorry, want to be stable. Okay, they want to be like a noble gas. Number 7, how many valence electrons are transferred from the potassium atom to nitrogen in the formation of the compound potassium nitride? So now this is where we're going to put potassium here. Okay, now this is just elemental potassium as it'd be on the periodic table. And nitrogen, we'll just put nitrogen right over there. But from our previous problems, we know that potassium, when it ionizes, when it becomes stable, it's going to have a +1 charge. And now I'm going to do those +1. We call this now an old-fashioned term. It has a +1 oxidation number, but that means it ionizes to a +1. And we know that nitrogen over here, when it ionizes to become stable, it has a -3 charge. Now, you can look on your periodic tables to see nitrogen's here. It needs 3 more to be like a noble gas. And that potassium over here, it needs to lose 1 to be like a noble gas. You can also double-check those if you needed to on your chart of ions. Now, potassium's not on here. Oh, there it is. Yeah, potassium is there. I take that back. And then nitrogen. Now, on this particular chart, I don't think we have nitrogen on this chart for the -3. But, yeah, we don't have -3, but it should make sense to you because it's got to gain those 3 electrons to become a stable anion. Anyway, so let's see. What does it say? How many valence electrons are transferred? Okay, so what's going to happen here when we do the crisscross method, so we're going to bring that 3, the absolute value of the 3 over there, and we're going to bring this over to there. Now, our compound is going to be K3, and we don't bother to put the 1, so there's tripotassium nitride if you like. So what's happened though is, remember, every potassium is giving up 1 electron. So since there's 3 potassium, 3 of these potassiums are giving up their electrons, so we've had 3 valence electrons given to aluminum. Given to the nitrogen. Sorry about that. So 3 valence electrons were given to the nitrogen from the potassium. Did I make sure I answered that? There we go. So we use the crisscross method to get us the chemical formula, and then that means that there were 3 of those given. And if you wanted to, if that's still not making sense, okay, if we have nitrogen, there's what its Lewis structure looks like, and you're going to have a potassium, whoops, that's supposed to be a potassium. Okay, the potassium is giving its electron there, it's giving another electron there, and it's giving an electron there. So now it thinks it's a noble gas, and they think they're each a noble gas. Number 8, how does calcium obey the octet rule? Let me scoot that over. When reacting to form compounds. Okay, so what happens is, again, because calcium starts off as a 2+ ion, it wants to get rid of those 2 electrons. And when it loses its electrons, okay, so calcium's right here, it's going to lose its 2 valence electrons out here. So what happens is now it loses its 4s electrons. It's going to have its outer shell now. It's going to be very much like argon electronically with the electrons, but it's going to have that +3 charge because it's got 3 more protons in its nucleus than argon does. Now, did I answer the question? So calcium, when it's reacting, it will give away these 2 electrons to atoms that need it. And that way it now has, in its next energy level, it has 8 electrons. What's the formula when these 2 create a compound? Well, this is the crisscross method, and you can look on your charts. I'm going to just make that a +1 because I don't like seeing that there. So we're going to switch that absolute value of the oxidation number now becomes a subscript, and this oxidation number becomes a subscript. And when we do this, they're the absolute value. So Na3, nitrogen 1. In fact, we wouldn't even really need to do that 1 down there. What's the formula when these guys create a compound? Well, once again, absolute value, crisscross method of the oxidation number becomes the new subscript for aluminum. The +3 oxidation number for aluminum becomes the new subscript right over there. And we're going to take, it'll take 2 aluminums, getting rid of 6 valence electrons altogether, and it'll take 3 oxygens because each oxygen needs 2 electrons, and this is the perfect mix because now you've got 3 electrons being given by the 2 aluminums, and you got 6 electrons being taken by the oxygens there. And that's when we form these compounds, we want to make sure that the givers and the takers have the equal amount of electrons they're given and taken. What's the name of the ionic compound formed from lithium bromine? So now, first off, you can look on your periodic table. Lithium, okay, lithium's going to have a +1 charge. And bromine is over here. It's a halogen. All the halogens need to gain 1 electron, so they're going to be -1. Or you could double check on your chart. Okay, lithium +1, and over here bromide -1. But they may not be on that list, so you need to know how to find them on the periodic table. Now, they both have a negative. They also both have 1. So the compound, the symbol for lithium is Li. The symbol for bromine is Br. And the crisscross method, there's just going to be 1 and 1, but we don't do that in chemistry. We leave it lithium bromide like that. So it's a 1-to-1 ratio because this one loses 1 electron, this one gains it. Oh, okay, and the name of that compound, sorry, I got off. It's going to be, lithium bromide. We make this end in IDE. We keep the metal's name and end it in bromide. Okay, so you got to practice there. What is the formula for this compound? Now, what I like to do, whenever you have a polyatomic ion, I think it's just a good idea. Let's just put parentheses around it to remind us that it stays together at all times. Now, when we do that, we just do the crisscross method, just like we would if this was just a regular metal cation. Non-metal cation. We're going to put the absolute value of this oxidation number here, and this is a +1. We'll put that over here. So this becomes trisodium. If you wanted to, you could call it monosulfate, but we can just call it sulfate. And there's just 1 of them, so we don't really need to put the brackets around it, but if it just kind of helps you see, we don't even need to put the 1 there, but so that's how that would be. What type of elements form ionic compounds? Okay, metals and nonmetals. Okay, that's what forms, or you might have said cations and anions. Oh, wait a minute. Cations and anions, okay? Number 14. Oh, we're doing about 1 minute a question. That's pretty good. Ionic compounds are normally in which physical state at room temperature? Ionic compounds, let's get our question over there so you can see it. At room temperature, they are normally going to be a solid, assuming you don't have them dissolved in water. Okay, now molecular compounds. Now this is, let me zoom out so we can see. Sorry, get my arm out of the way. Now it's real important. Whenever you see the word molecular compound, you got to be hearing a bell going off in your head, and this bell needs to be saying covalent bond, covalent bond, covalent bond. Okay, so molecular compound means covalent. Okay, covalent bonds are found in which states? They're found, okay, covalent bonds are found in the state of California, Florida, and Mississippi. Oh, just kidding, okay, no, meaning what states of matter, okay? So, molecular compounds, they can be solids, like a sugar. They could be liquids, like water. And they can be a gas, like, oxygen and nitrogen, like air. Okay, now the reasons for that, I think it comes up later, but there's the energy level, the bond energies holding covalent compounds together are not as strong as those electrostatic forces that are holding an ion together. So covalent compounds can commonly be found in those states of matter at room temperature, whereas ionic compounds, okay, they're going to be solids. And again, what causes this? For the ionic compounds, they have those strong electrostatic forces. And the electrostatic force is strongest in those in ionic bonds because you have a pure plus charge, and say in salt, a pure negative charge, and that's super duper strong. Now, when we have the partial charges in some of the covalent compounds, they're partial charges, okay? And I think in class we use the illustration of those big giant magnets I have, okay, clanking together over here could be representative of an ionic bond, but then those little tiny round magnets that we stick stuff on, okay, they're kind of attractive, but they're easy to pull apart. That was what we were using as an analogy for that one. Number 15, which of the particles are free to drift in metals? Okay, now in metals, we've got electrons, protons, and neutrons. Well, these guys are tied up in the nucleus. They're not going to go anywhere, okay? Electrons are what are free to drift around. Now, remember, when we were doing our little demonstration with the eye, okay, so the idea there was that if over here, if this is a metal, and my hand here is a metal, and over here is a non-metal, okay, this non-metal over here, okay, it really wants an ion, okay, and so this metal wants to get rid of it, and so there we go. They're happy. He's stable now. He thinks he's a noble gas. They're stable because this electron was given from one metal to a non-metal. Now, when we're talking about covalent bonds, we've got two nonmetals here, and these nonmetals, okay, they both want electrons, okay? They don't want, so what they have to do is they guess, okay, look at here, we can share these, okay? Now the thing is with a covalent bond, these two atoms, when they're sharing these electrons, they're sharing them. They're locked together, sort of, by this. Okay, so they got to share it back and forth. You know, if we want to go like this, okay, they're sharing them back and forth. Now, with the metal bonds, though, now metals, they're kind of like covalent, except, okay, the electrons, they can share electrons with anybody. Okay, these two atoms, if these are two, gold atoms, they can share their electrons with gold atoms all over the room. And so those valence electrons, they can just go everywhere. They don't, these valence electrons, they're not locked into being just with these two guys. They can go all over a place, and it's like an ion, it's going away. So, did I answer the question? Which of the following particles are free to drift in metals? It is electrons. Let's see, number 16. What force holds ionic bonds together? Okay, back over here. Electrostatic forces. So electro means you got a plus charge, like I said, with the sodium, and it's being strongly attracted to the negative charge in a chlorine. Okay, these are charges, but they're static. They're not flowing like electricity, hence the word static. Okay, they're not electric current that moves through wires and stuff. This right here, they've got a plus charge and a minus. They're going to come together, but they're not going to necessarily move. So electrostatic forces, very strong. And they're involved also in covalent, but because these are opposite charges, they're attracting. Remember, with covalent charges, you're going to have like two chlorines coming together, and chlorines tend to want to gain electrons, and so what's going to happen is they don't really want to be next to each other unless they can say, okay, I'll overcome this negative repulsion if it gives me a full outer energy level, so I'll kind of tolerate being near you over here, but it's fairly easy to break this, where it's not easy to break, as easy to break this charge here. How do atoms achieve noble gas electron configurations in single covalent bonds? So when we have single covalent bonds, probably the easiest one is just going to be water. Okay, we've got oxygen with this here. We've got a hydrogen right over here with its electron. I'll make it an X so we can tell it. And we got another hydrogen right there. So what happens here is, because these guys are sharing, and what will happen is, for a fraction of a moment, okay, oxygen thinks it has 8 electrons around it, thinks it's a noble gas, and then the next fraction of a moment, those two hydrogens think that they have, there we go, they think that they have 2 electrons, and they think they're helium. So that's how they achieve it, because they're sharing electrons, and it happens so fast, at any instant of time, you can almost say they've each got their octet, or in case for their hydrogen, it's duet rule filled. They've got all the electrons they need. Why do atoms share electrons in covalent bonds? Okay, they share them because they need to fill their outer energy levels, and they don't have a metal around to give them one. Okay, so they have to share covalent because there's no metals around, no metals to give electrons. So what has to happen is they have to compromise. Okay, so you've got hydrogen over here, and it's got another hydrogen there. They say, okay, we don't like these negative charges being near each other, so what we'll do is we'll kind of team up. And usually when these get flying around, what's going to tend to happen around there is that you're going to tend to have one electron will be over here, and the other one's going to do its best to be as far away as possible, and that happens, you know, a million, billion, trillion times a second. Draw the Lewis structures for the following. Well, I'm not going to draw them out now. We've done it in class. I've kind of pre-done these. But the idea here is now with the oxygen, you can pause these if you need. So when we put these two Lewis structures together, it's real obvious those two are sharing, and then over here, those two are going to connect together and share, and I'll actually connect those. Those two are sharing right there. If we clean that up, it'll look like this. So that would be the Lewis structure for oxygen. For chlorine, okay, now I've drawn these in different colors. Let me zoom in here so we can see a little bit better. Okay, so here's the Lewis. I mean, we've got 2 chlorines. They're sharing those electrons. You could redraw it if you liked, like that. I'm not going to do any more of those because I got to save time, but you could do the Lewis structure there. With nitrogen, when you start to draw nitrogen, oh, and I forgot, oh, heavens to Betsy, I left off that one. There we go. So it's pretty obvious those two are going to team up, and then these two unpaired electrons will team up, as will those two unpaired electrons will team up. And now you've got this one thinking it's got 8 electrons, and this one thinks it's got 8 electrons. Fluorine, okay, it's going to share, they're going to share that one electron with each other. Now the next part here, oxygen, -2. Well, I've drawn the Lewis structure for oxygen. When oxygen gains another electron there and there, now we've got the octet rule. It has 8 electrons. It's stable, but it's got a -2 charge because it's got 2 negative charges up there. Here's the Lewis structure for nitrogen. Okay, it's going to gain 3 electrons to become stable. And so when it gains 1, 2, 3, which I'm drawing instead of dots, I'm doing the negative signs here to let you know those are negative charges, it now becomes a -3 ion. Calcium starts off like this, but remember, calcium's a metal. Okay, there's the Lewis structure for calcium. It's going to lose that electron. It wants to get rid of it, and since it's losing 2 negative charges, that means it's going to have more protons than electrons, and it's going to change into calcium 2+. Did I draw that? So the Lewis structure, now what we do is a lot of times for the Lewis structure, when we show that we've gotten rid of those, technically you could do calcium 2+ would show the Lewis structure, but if we put a bracket around it, the bracket is just saying, hey, we've removed or gained electrons here. For lithium, it has this 1 electron over here. It wants to get rid of it. Okay, it gets rid of that 1 negative charge, which means it's going to be lithium with a plus charge. And one way you can designate that this is the new Lewis structure, they're saying its outer orbital is now empty. There's no electrons there. Its next lower one is full, and for lithium, it's going to think it thinks it's helium, but it's got a plus charge. Which of the following represent ionic? Ionic bonds are metals. Over there, ionic. They're metals bonding to non-metals. So these are both metals, so that's not ionic. Here's a nonmetal. Wait, let me rephrase. That's a nonmetal and that's a nonmetal, so it's covalent. And two more nonmetals bonding together. Okay, it's covalent. Barium is a metal. Oxygen's a nonmetal. Okay, there is an ionic bond. Carbon and sulfur, those are both nonmetals, so there's only one ionic compound. The other ones are covalent. Number 21 says, which of those compounds represents a biological, okay, so they're made in living things, molecular compound. Molecular compound, okay, whenever you hear molecular compound, a bell needs to go off in your head saying, hey, that's covalent. Okay, so, barium and oxygen, hey, that's ionic. Sodium and chloride, hey, that's ionic. Non-metal, 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 hey, that's covalent, C6H12O6. You'd better remember that from last year in your biology classes, because that's our friend glucose, the fuel for our bodies and what plants make to begin the storage process of sugar. That is very definitely a biological material. Now, this is also covalent. But C4, that's going to be butane. Butane. Oh, wait, butane. Okay, see, I've got a thing here for butane. Oh, I had butane here. Oh, come on. I had a butane lighter a second ago. So anyway, butane is, with that one, it's not formed regularly in compounds, in biological compounds. All right, so moving right along here. We've got... Oh, so the answer is that one there. Molecular compounds are made from bonding. Okay, you can have a couple of things here for this one. So you can say metal with a nonmetal. Okay, molecular. Oh, excuse me. Non-metal with a nonmetal. Okay. Oh, molecular compounds. Remember, the bell's got to go off. Okay, molecular compound. You've got to be seeing that in there. So that's covalent. Made from bonding nonmetals with nonmetals. Number 23, which of the following formulas represent a covalent compound? Okay, sorry for the moving around. Okay, these are all nonmetals. That's covalent. Beryllium is a metal, and that's a nonmetal. That is ionic. Zinc is a metal, and that's a nonmetal, so there's only one covalent there, sulfur dioxide. Ooh, that puts the stink. Okay, in rotten eggs. All right, now, ladies and gentlemen, here's the next one here. We've got, how does oxygen obey the octet rule when combining to form compounds? Well, what oxygen's going to do here, here's its Lewis structure. Okay, oxygen's going to gain 2 electrons. It's going to pull electrons from other atoms, and now if it in an ionic compound, it'll just take them, but if it's with another oxygen, it'll say, okay, we've got to share these, so it will share, it'll take if it can, but it'll also share electrons from another one. So now it has 8 electrons out here, and for the moment here, that one has 8 electrons out there. Under what conditions can potassium bromide, that was earlier, we had potassium bromide, so we had that earlier, conduct electricity? Potassium bromide is a ionic compound. And ionic compounds can conduct electricity. That's part of their characteristics, but only when they are melted or dissolved in liquid. Sorry, that's terrible. Melted or dissolved. And the reason is that when they're either melted or dissolved, okay, their plus charges here, they can migrate, they can move the bromines will move to a positive electrode, positive end of the battery. These can move towards the negative end. They conduct their charges with them, and it can be ionic. Excuse me, it'll be, because they're ionic and they're either melted or dissolved in water, they can move towards their opposite charges, and that allows electricity to be conducted. What is the charge of NaCl as an ionic compound? Well, the sodium part of it is plus, and the chlorine part of it is negative. But together, it's going to be a great big neutral. They're 0, electrically neutral. Now, inside of it, there's those plus and minuses attracting, but on the outside, it's a neutral compound, and that's what all bonding does. All of these elements on the periodic table, chemistry is really about all of these elements trying to be like these 6, and they'll do all sorts of stuff to do that. What causes dipole? Now, you got to remember, anytime we see the word pole or polar, we got to think there's a plus side and a minus side. Or at least there's a partial plus side and a partial minus side if we're talking covalent bondings. And what causes these dipole interactions? Electronegativity. Electronegativity. Which again means some elements pull electrons with greater force. The nonmetals need electrons. They have higher electronegativities. And so in a compound where you have, let's say, a halogen, which are strongest, like our friend chlorine over here, has a fairly high electronegativity. If it's in a bond with something like, let's just do little old, lithium here. Lithium has a very small electronegativity. So what's going to happen is lithium's electron is going to tend to be kept over. Oh, wait, my mistake. Sorry, I did it. Pardon me. That was an ionic compound. I should have said hydrogen, which is a nonmetal, and chlorine. Sorry about that. I started to go down the wrong track. Okay, very high electronegativity. The one electron this is giving is going to spend most of its time over here. Occasionally it'll fly over there, but most of the time over here, which means all hydrogen has inside of it is one proton. So this is partially positive. And since that electron is spending most of its time over here, this is going to be partially negative over there. So that's why, and we call that a dipole, because it's polar now, okay? There is a plus and a minus side. And that's all dipole means, 2 poles, plus and minus. It's a fancy way to say polar. Number 28. Covalent compounds are made between which two? Okay, between nonmetals. What happens with electrons when an ionic bond forms? Okay, well, you've got electrons are given or taken. Given by metals, taken by nonmetals. And number 30, metals form blank and nonmetals form blank when they bond together. Well, you could say when metals, you can say that they make cations, if it's ionic, and nonmetals form anions, if you like. Metals form, I think that's really it. Metals form blank and nonmetals form blank when they bond together. So you can either get cations and anions. You could say that they're going to form a stable compound because they have the same number of electrons. Excuse me, take that back. They're going to form a stable compound because they're sharing the enough electrons that they end up having a full outer shell. So, but I think the best one, metals form cations, nonmetals form anions when they bond together. And if, there you go. I think we're done. I'm tired. Sorry for the long lecture here. Going to end it right now. Bye. Done.